If so, you are probably aware of the dizzying effects of high altitude on your body. As you climb higher and higher, less oxygen will be available. A lack of oxygen is called hypoxia. Hypoxia is potentially dangerous. As you climb to altitudes above sea level, the air pressure is lower. Since it is air pressure that forces oxygen into your lungs, if you have less air pressure, you will have less oxygen getting into your bloodstream. As you climb higher and higher, there will be less oxygen in your blood. Your tissues won't receive as much oxygen. The tissues most affected by this lack of oxygen are the brain and your eyes. Pilots must be able to recognize the possible signs and symptoms. Onset of hypoxia is subtle. Hypoxia gives a false sense of well-being, and the symptoms differ from one individual to another. Some of the signs and symptoms are blue fingernails. Decision-making ability is decreased. You can become euphoric and feel like everything is okay. Your vision is impaired and you can experience memory loss. Also, you can start to hyperventilate. It is essential that you recognize the symptoms of hypoxia and descend to a lower altitude or use supplemental oxygen if hypoxia is suspected.
Alright, next problem. A bag of potato chips is packaged at sea level where the atmosphere, it's 1 atmosphere, and the temperature is 25 degrees C. So P1 is 1.00 atmosphere. T1 is 273 plus 25, which is 298 Kelvin. And V1 is my original volume of the potato chips, which is 315 milliliters. Now you're allowed to stay in milliliters. Just remember that your new volume that you're looking for, because again the question here is what is the new volume, will be in milliliters, not liters, when you're finished. Okay, what's my next data? If this bag of potato chips is transported to Denver, where the pressure is 0.775 atmospheres, and the temperature is 20, what is the new volume? Well, we already have this rearranged here. It's the same, right? V2 will be P1 V1 over T1 times T2 over P2. And that will be 315. Remembering my answer is going to be in milliliters. T2 is 293. T1 is 298. And P2 is 0.775. When I do 1 times 315 times 293, enter, divided by parentheses 293 times 0.775, close parentheses, I get 400 milliliters. And I'm going to draw a little line over this 0 because I have 2 sig figs. So I'm trying to communicate that this one counts. So 2 sig fig answer, 400 milliliters. That is the combined gas law. Using lots of data to get your answer, it merges all the ideas of Boyle's, Charles, and Gay-Lussac's laws. Before we leave the topic of exploding bags of potato chips, here's a blog called Elk Jerky for the Soul. It's about their experiences buying chips in Lubbock, Texas, and traveling to Washington State or Colorado, and the chips apparently explode. You have to buy chips packaged for the altitude in which they'll be consumed. The next gas law that we're going to consider is the ideal gas law. PV equals nRT. What is N? N is moles. And in fact, the biggest clue that this is the right gas law for you to use is that the word moles appears in the question. R is a new thing, and that is the ideal gas constant. It is a constant. It has a value of 0.0821 with strange units of liters times atmospheres over moles times Kelvin. Now that looks scary, but it basically just makes the equality work. And then finally, remember to stay in Kelvin in all of the gas law problems so that you never divide by 0. So, what is an ideal gas? An ideal gas, by definition, no interaction, no bonds, and small, and spread far apart. That's an ideal gas. No interaction between the particles, and then we would say they would abide by this relationship here. All right, so let's do some ideal gas law problems. The first problem is if I have a 50-liter container that holds 45 moles, there's the first time you've seen moles in a gas laws question, there's your N, at a temperature of 200 degrees Celsius, well, we immediately switch this to 473 Kelvin. What is pressure? This is volume. PV equals nRT. I know everything because I always know R. R is 0.0821 liters, atmospheres, over mole, times Kelvin. And no, you do not need to memorize that. What is pressure? Pressure will be nRT over V. I'm just rearranging that to isolate pressure. N is 45 moles. R is 0.0821 liters, atmospheres, over mole, Kelvin. Temperature is 473 K. And volume is 50 liters. When I multiply 45 times 0.0821 times 473, enter, divide by 50, I come up with 35 atmospheres. And I just want to take a moment to look at the units. I have liters canceling liters, and I have moles canceling moles, and I have Kelvin canceling Kelvin, and I am indeed left with atmospheres, my pressure unit. Next problem. How many moles, we're looking for N this time, are in a 30-liter, there's my volume, scuba canister if the temperature of the canister is 300 Kelvin and the pressure is 200 atmospheres? I'm solving for N. N would be pressure times volume over RT. Pressure 200, volume 30 over 0.0821 times 300. And if you are slick, you see, 30 on the top, 300 on the bottom. Simplify this by just making that worth 10 down here. So I'm really going to divide 200 by 0.821. Cleans up your math a little bit. You get 244 moles. That's a lot of moles. I want to mention one thing before we leave this screen. There is another form of R that is when pressure is in torr. And it's simply this number times 760. And it will appear as this. R equals 62.36 liters torr over mole Kelvin. You see it's identical in the units except for this torr switch for atmospheres. And if you take this number times 760, you'll get that number. Okay? So those are the ideal gas law problems. They are the only ones that moles show up. And that's always your clue in the word problem, is that you'll see the word moles. The next gas law that we're going to look at is Dalton's law of partial pressure. This is the same John Dalton that came up with the idea of atoms being the building blocks of nature. It's a really simple concept that since gases behave like particles and they really don't maintain any particular identity, it really is a matter of count, we can sum the pressures of the various gases to come up with the total pressure. So in this problem, if I place 3 moles of nitrogen and 4 moles of oxygen in a 35-liter container at a certain temperature, what will the pressure of the resulting mixture of gases be? It's saying I don't have to do 2 separate problems here. There's a total of N equals 7 moles. I can lump them together because they have the same effect, no matter the identity of the gas particle. So that's my N, and here's my V, 35 liters. Temperature of 298 Kelvin. What is pressure? Okay, so pressure is nRT over V. I go to that gas law because I'm working with moles. And so you plug in here, 7 moles. Since my pressure unit is not identified here, I will use my favorite R value, which is the 0.0821 liter atmosphere mole Kelvin, and as a result of that decision to use 0.0821, my answer is going to be in atmospheres. 298 Kelvin on the temp, and then your volume is established as 35 liters. When I multiply 7 times 0.0821 times 298 and divide by 35, I come up with the answer of 4.9 atmospheres. Next problem. You perform an experiment to produce oxygen gas by water displacement. Do you remember your lab? You collected gas by water displacement. The lab is under STP conditions. Tell me, what is STP? Right, STP is 273 Kelvin and 1 atmosphere pressure. You measure total pressure inside the collection vessel to be 1.5 atmospheres. That's P total is 1.5. The partial pressure of water at 25 degrees C is this, 23.8 millimeters of mercury. Well, I can't mix atmospheres with millimeters of mercury, so let me convert this to atmospheres so I'm apples to apples. I'd take 23.8, I'd divide it by 760, and I'd come up with 0.0313 atmospheres is the portion that's from water. So this P total is the oxygen pressure plus the water pressure. But now I know this is 1.5 atmospheres, and this is my X, and this is 0.0313. And when I solve for pressure of oxygen gas, I get 1.47 atmospheres. In our last 3 minutes of this video, we want to expand your skills with respect to solving stoichiometry problems, because through PV equals nRT you now have a third way to find moles. Let's remind ourselves how we have found moles in the past. Do you remember when we first did stoichiometry in Chapter 8, when you had so many grams of a reactant, you would turn it into moles using the molar mountain, and then you would connect the moles corner of the reactant to the moles corner of the product, and you would multiply by the coefficient bridge as you transferred between the two compounds. So by getting to moles, we were able to relate one compound to another, and then you would finish up and multiply these moles by the molar mass of the product and come up with the grams of product. And this is something that stoichiometry makes chemistry really practical, because we always care about how much product we can make. Well, another way that you were able to find moles is if you knew the count. Like if you knew the number of atoms, you could always divide by Avogadro's number, which is 6.022 times 10 to the 23rd. That's the second way you know to get moles. And we usually use little n as the symbol of that. So we are now adding a third way through PV equals nRT, or n is PV over RT. So you have 3 ways to get to moles. So now your stoichiometry problems can be a blend of giving you grams of one compound and asking you how many liters of a gas you'll get on the other side. And that's the case we have here. How many grams of calcium carbonate will I need to form 3.45 liters of carbon dioxide? So that's my goal, and the question is how many grams. So it's going to be a blend of using a molar mountain on the left and PV equals nRT on the right, and going from moles to moles. So let's turn this into a molar mountain. And I don't know if you remember, calcium carbonate has a really slick molar mass of 100. So that will come in handy later. Right now, we have to get to moles through the 3.45 liters. So we are at STP, and this question failed to say that. We're at STP. So PV equals nRT. So my moles of CO2 gas will be 1 atmosphere, 3.45 liters, 0.0821, temperature of 298. When I run those numbers, I get 0.12 moles of CO2. What's the next step? Right, you need to go to the coefficient bridge. What's my coefficient bridge for this problem? 1 to 1. Okay, so that means we're going to have 0.12 moles of calcium carbonate, multiply that by 100, and you'll get your answer of 12 grams. Next problem. When chlorine is added to acetylene, and this is acetylene, next problem. When chlorine is added to acetylene, here's chlorine gas, here's acetylene, C2H2, it's C triple bond H. That's acetylene torch, acetylene gas. You get 1122 tetrachloroethane. Okay, that's this. 4 chlorines in addition to the 2 hydrogens that were there. The question is, how many liters of chlorine will be needed to make 75 grams of the tetrachloroethane? Okay, so what do we know here? We have what do we know here? We know we want to make 75 grams. That's our goal. So that's really sitting at the top of a molar mountain since that's grams. I added up the mass of this. It's 166 grams per mole. What I don't know is moles. So that I can calculate by dividing the 75 by the 166, and I get 0.45 moles. What would you do next? The question is, how many liters of chlorine? Okay, that's my question. How many liters? Well, the only way you know to get from moles to liters is through PV equals nRT. What's our multiplier? One of these makes 2 of these, or 2 chlorines are needed to make the tetrachloroethane. So I need 0.9 moles of chlorine gas. Again, I failed to mention that this is at STP. So we would say N is 0.9, and we're looking for volume, so it'd be nRT over P. N is 0.9, R is 0.0821, temperature 273, pressure of 1 atmosphere. And you'll come up with a volume of 20.2 liters. Hopefully, remember the basic definition. Remember that stoichiometry is all about quantifying one compound to another, and we relate through moles, and now you have 3 different ways to get to moles. You can do it through grams, you can do it through volumes, and you can do it through count of atoms, which is actually rarely done in this class. It's not practically done. So hopefully you can practice that until you feel confident that you can handle any type of stoichiometry problem. Thanks for your attention, and great job working on your gas laws.